Good morning. Once again, the physics video lecture. This is Physics 105A video lecture 28. So we're back to Newton's law, motion of a particle under forces. And we had two really good examples. I'm going to review those before we move on. And in fact, for one of them, I owe you a discussion of the cycloid. But let's just take it in order again. We were working with mass times acceleration, general case of force and position, velocity and time. And the first example I had introduced was, and I'll just write it out in this form, we had gravity. So this, with G pointing down, this would just be projectile motion. But we also had a force of friction. And I'll make K a positive coefficient, that's V. How about I write that as R dot? Good, so we wrote that out last time and we want to solve this. I'll just say a couple more things about the solution. So in the plane, we did this with two components. In the case where K is equal to 0, this is your standard projectile where if you had V0, projectile launched at an angle theta, you would get a nice trajectory like that. In fact, I can write down what that would be. So for K equals 0 and these initial conditions here, Y would be equal to tangent of theta times X minus G X squared over 2V0 squared cosine squared theta. Right, so that's that famous result. By the way, make sure you know how to obtain this. Just as a matter of course, you guys should be able to do that. So yeah, that's that case. Now with friction, so when K is not equal to 0, and you have this linear friction law, you're going to get a qualitative difference. There's going to be some maximum distance that's attained, and you no longer have a symmetric trajectory. You get something that goes up and then falls down and never quite reaches this asymptote. So this is K not equal to 0. And what we were going to do is just find x of t and y of t, and if possible we'd put together y of x, but it's not going to be that pretty. It's going to be pretty complicated. Okay. And the x of t of y of t were actually functions that we had seen before. So it's a nice example. Good, that was our first example, and that's homework. The next example is also homework. I think we'll postpone it, the due date till next week. But yeah, what was the second example? This was the Lorentz force. So here we had also a velocity dependent force, but we had QE plus Q V cross B. I could write R dot again. Q R dot cross B, and we decided to go like this. So this would be X, Y, and Z. We're going to restrict the motion to the XY plane. We're going to have a uniform E pointing in the Y direction and a uniform magnetic field pointing out. And under those circumstances, I claim that we're going to get a curve that goes like this, a trajectory. Very interesting, right? charged particle, it starts, you know, if we start from rest right here was the idea, it gets pushed in the y direction, but then of course this force kicks in and bends it over, actually brings it to a complete stop. If you start from rest, the more general solution, which will be available to you, is that it would do loops of the loop like this, but if you start from rest, you actually get a cycloid. So I have to explain the cycloid. It's possible I would have typically done it at the beginning of the semester, but I'm pretty sure I didn't do it this semester. So anyway, this is the cycloid, and I'm going to discuss the cycloid now. Because this is a really interesting curve. The way it's generated is following. Imagine you have a wheel of radius r. Here, let's draw a better wheel. Start with that perfect circle. Okay, got a wheel of radius r, and we're just going to roll it along the x-axis. And if this is the point on the wheel that we're following, as this wheel rolls forward, it traces out a curve that looks like that. So what we have to do is get the parametrization of that curve. And that'll work like this. So let's go ahead, have a y-axis here, and imagine that this wheel has rolled forward. Actually, we're going to do it in 2 steps. Just imagine that this wheel is turning about a fixed axis right there. Okay. Then, when that point gets right there, we would say its x component is equal to minus, put radius there, minus r sine of theta. And its y component would be r minus r cos theta. Okay. So that would be if it were fixed. All we have to do is add to this r theta for this uniform rolling motion forward, right? When theta is equal to 2 pi r, and this thing is moved this distance. And the interesting thing is, this point here, if you allow the wheel to roll, goes like this. Sometimes if you see a bicycle at night with reflectors in the spokes, you'll actually see this kind of a curve being generated. If you see, you know, in your headlights, for example. Be that as it may, let's formalize this. I'll just rewrite them. So the cycloid, we have x, and okay. So for the wheel rolling with theta equals omega 0 t, right, with some angular frequency times t, we can now write out x of t is equal to r omega naught t minus r sine omega naught t, and y of t will be equal to r times 1 minus, or r minus r cos omega naught t. See, so this was the parametric expression for the cycloid. And if we're doing some kind of dynamics, then we turn out to have theta rolling out uniformly, which it doesn't have to do, but in that case it would be theta equals omega naught t. Well, the fact is, when we set this up the other day, we already had found an omega naught. Okay. We had already found what the omega naught was going to be. I'm just going to write here, recall omega naught was equal to B0 over M. And you'll find when you continue integrating the differential equation and taking those initial conditions, remember initial conditions were that we start at the origin with 0 initial velocity. So if you do that, you'll find something of this form, and really you're just going to have to find out what that R is. So I'll recall, maybe that was this, find the radius here. It's going to depend on everything. It's going to depend on Q, M, B0, and what I had in there, E0 as well, right? So yeah, you're going to find that, whatever that radius of this thing here is, in terms of these parameters, and you'll be done. Very excellent, interesting, and satisfying problem. So yeah, enjoy that one. So you've got this one, if you're not done by this week, turn it in next week, no problem. But that was also homework. So these were both homework. Okay, so both of these we had functions of effectively R and R dot, although with this constant in this case, that's kind of a trivial dependence. And here it was a constant as well. But our next topic is, as it was before in 1 degree of freedom, functions, forces that are just a function of position. Okay, so forces that are a function of position only. Numbering things? Yeah, why not? So next. Forces F is equal to F of R. And we hopefully remember what we had in the past with 1 degree of freedom. This has to be a generalization of that. So 1 dimension, we ended up immediately getting a potential energy, and that's what we're going to do here as well. But first of all, we'll write Newton's law. F of R. So we're going to define the potential energy U of R is equal to minus the integral F of R dot dr. Well, this has to be an integration variable, so we put a little prime on it. And the upper boundary is R, A is some point that we're free to choose. So this is just like the 1-dimensional case, but it's a more complicated object. This would be a line integral along some path in space. So if we're out here in space and there's point A and here's point R, then we integrate along some path, some contour, and when we get there, that's the point R. So in order for this to be a reasonably defined object, it has to be independent of the path we take. So if that's the point R here, then this path has to be just as good. It has to give the same answer. And that restricts the type of function that we can use as a force and define a potential energy. So we're going to deal with these things in more detail. Okay, we'll spend some time with the integral theorems and do a little calculation with this. But right now I'm just going to say, okay, it's defined that way. And what we have, if U of R as defined right here by equation star, if that's uniquely defined so that it's independent of the path taken, path independent, then what we have from this object here, f of R is equal to minus the gradient of U of R. So we have to get into some vector calculus on account of this as well. Like I said, we're going to do some integral theorems. Of course, we have to know some derivative rules. R vector. But the point is, if we have this property, then we can set up energy conservation, same way we did last time. So that's what I'll continue with. Okay, so where are we? Good, and like I said, we're going to prove all these things and go through them. But we have this now. So now define the energy E as 1/2 m r dot squared plus U of R is equal to E. So this R dot squared vector is defined as the scalar product of the velocity vector with itself. And for example, this would therefore be x dot squared plus y dot squared plus z dot squared in Cartesian coordinates. And now we'll take the and differentiate with respect to time. With respect to time, what we get here, so d over t, what we end up with is m r dot product with r second derivative plus the derivative with respect to time. Here we have the chain rule. It's going to be gradient u of r, and the inner derivative is dr dt. So I've taken the complete time derivative of the left side of this equation, and I get, if I factor out r dot, take a dot product, I get m r acceleration. And I factored this out. Now this gradient is minus the force. Okay. So minus f r, and of course by Newton's law, which we're starting out with, right, then this is equal to 0. Equals 0, and then we can say that this energy is conserved. Okay. Conserved or constant or conserved, and E is conserved. So we just have to justify all these steps so that we really know them. I just went through them symbolically and everything's right. Everything's correct here. But for example, and you want to make sure you see this dt of our r dot squared is the complete time derivative of this x dot squared plus y dot squared plus z dot squared. And each of these we can do individually. We have 2x dot x double dot, and then the same thing for y dot and z dot. Z dot z double dot. And we can and we should then, here, let's work up there, recognize the scalar product, right? That is now 2, and then x dot x double dot y z z, let's write that a little more clear. We've got the 2, and that would be the r dot dotted into r second derivative, okay? Which is, of course, what I used right there. I had a half, so I canceled the 2, 2 cancel the half there. So yeah, so we've definitely taken care of that. What about this gradient dotted into r dot? So for that, we also need the chain rule. The chain rule of multivariable calculus. So let's send this up. So I said I was taking a complete time derivative, right? Differentiate with respect to time. So let's look at that a little closer. So d over dt, just to be really explicit about it, of u of r of t. Okay. That's what we just did and claimed that it was the gradient dotted into the velocity. So we'll write that out once more in this way: u of x of t, y of t, z of t. Now the chain rule of multivariable calculus is that we treat it as though there were just one of these things here, and then we sum over all three of them. So what we have here is partial u with respect to x, and then partial, or not partial, but then dx with respect to t, and then we do the same thing for y and z. So that's how the chain rule works. That's a u, that's a y, and then du, dz, dz, dt. And then you recognize those are the three components of the gradient, and they've been dotted into the three components of velocity. So that is gradient of u of r dotted into the velocity. Okay. Good, so that is what here I just wrote it out quickly, and here I'm showing you explicitly exactly what the calculation is. So yeah, you definitely want to recognize this, and you do it often enough, of course, you just see it and knock it out in that form. Now the only question, or not the only question, but the question now is, how about this? So right here next, what about that potential energy function itself? I'll even write it out. What about u of r being this line integral and the fact that I just claimed that the gradient of this is equal to, you know, minus the force. So that's the next thing we have to tackle. Let's check the time here. Okay, great. Question mark. What about this one here? So this takes us back to some actually, you know, to some vector analysis and integral theorems. So we need to talk about the conditions on this thing for this really to work. And we'll do that step by step. Okay, let's see. I think first I'll just discuss the integral theorems. So we need to know the conditions on which we can call this, you know, a function whose gradient gives us the force. We needed that uniqueness. So let's just right here recall the integral theorems. And in a sense, there's only one integral theorem, but I'll write them all out. The first one I'll write out is that integral of just some f prime of x dx on an interval a to b, f of b minus f of a, right? That's one we'll never forget. But what about in higher dimensions? Let's number these things. Second one, and we're going to reduce the second one to this first one, would be the one that's implicated up here, namely integral, I'm going to write vector a to b, gradient f of r prime dot dr prime is equal to f of b minus f of a. Okay. So then we actually have to know how to do a contour integral. Okay. But this one looks so much like this one. And now this a and b are points in space. Let's even draw our picture. So here we had x, a to b, right? We know the integral, the area of the curve, right? This one here would be 2 points in space and some contour to get from a to b. That would be that integral. And that will actually, roughly by this calculation up here, do that. In fact, maybe we should do the proof right now. Proof. Let R of tau be a parametrization. So such that tau sub A is less than or equal to tau is less than or equal to tau sub B. So this is a parametrization. And we always have an example for that. We just did the cycloid, right? The cycloid was a parametrization, and our angle went from 0 to 2 pi. Okay. but I'm just using different letters. Tau sawed off t be a parametrization of a curve in space with r of tau sub a is equal to the point A, r of tau sub b is equal to the point B in space. Let's see, I'll work up here. So then we have this integral here, a to b, which is the symbolic form, gradient f r prime d r prime. So what I'm saying, that's the line integral with this parametrization. So that would be the integral of d over d, not t, just using tau, tau sub a, tau sub b, d over d tau of this f of r of tau d tau. This, by the way, is very important. You can say that defines how to do a parametrization and an integration like that. And the proof of this, or this calculation here, not the proof, but the explanation of this is really what I did in the chain rule up there in blue, okay? So again, make sure you know that. But this now is of the form of this, which is of course our fundamental theorem. Okay. So that is f of r of tau sub b minus f r tau sub a equals f of b minus f of a by construction. Okay. So I'll just check it out. That's the proof. So this is how you actually do an integral of this type. Oh, actually not so fast. Well, yeah. Let me go ahead and put another step in here. So this integral here, this one I want to make sure we see. We'll do it in blue. I did kind of skip a step in terms of wanting to show you how these are done. So this here, by the calculation up there, is the gradient f of r of tau. We're putting all the gradient dotted into d r d tau d tau. Okay. Tau sub a, tau sub b. So you can say I should have gone from here to here, and then to there, and then to there. So yeah, basically this, dot product into the dr, which was just your little increment along these paths. These are your little infinitesimal drs in the sense of a Riemann sum. That substitution is dr over d tau times d tau. For physicists, this is completely intuitive, because this is a tangential vector. It's like a velocity vector, a tangential vector, integrating over d tau. So once you go from here to here as the definition of how to really do this, to get your parametrization, then from this here, you recognize this expression as being the complete time derivative of that function, the way I did it up there, and then boom, you're done. Okay, so that's our second integral theorem with the line integrals. Let's check our clock here. Good. So what's the third one? The third one we're going to do is the Stokes Theorem. So 3, we're going to say the integral of the curl of a vector f dotted into a surface normal V area. So I'm showing you Stokes' integral theorem. So you've got the curl of the vector dotted into a surface normal. I'll just write area here. Is equal to the line integral of that vector dotted into dr. And this symbol here means the boundary of that surface. Okay. Closed integral. So if we had, you know, the math books, you got some kind of potato chip surface there, and you have your oriented line integral around it, and you've got, you know, your surface normal, and you've got some vector field, okay, that type of thing. Okay. So this one actually brings us, and you know what? Let's go ahead and just call this capital F. It's just a letter, but in honor of the force we're about to talk about. Now here's the thing, this was a closed path, okay, right here, and this is an arbitrary surface now. Therefore, any path we take from one point to another, say I call this A, and this B, we've got a path independence. I could have come up here around the right side, or I come up around the left side. I'm going to get the same answer if going around the whole circle makes it equal to, not circle, whole circuit makes it equal to 0. That is to say, if this integral is always 0, then I have the path independence. Okay. So this was our force integral we were talking about earlier, done around a complete circle, so from A to B and from B back to A. Okay. Now, if that's always 0, then the left side is also always 0, and the condition on our force is that its curl vanish. Okay. So if this holds, so if this integral f dot dr equals 0 always, then so 0, let's make sure we write that out for arbitrary surface. Okay. Then the curl of f equals 0. Okay. Curl of f equals 0. And the other direction of the implication is also true. Okay. If the curl is always equal to 0, arbitrary surface, this integral is always equal to 0, then this path integral is as well. And that will give us the path independence. So the condition on our forces is that they be curl free. So for our, and we'll end the hour with that. For this integral here to be path independent, it's necessary and sufficient that the curl of F vanish, okay? Must vanish. So that's what makes this definition legitimate, okay, functional. The force that we have has a vanishing curl. Okay, we'll leave it at that for today and continue on next week. Okay, see you guys next time.